I would like to introduce Dr. Claudio Pinhanez, who is a scientist and inventor. Dr. Pinhanez currently is the manager of the Conversational Intelligence Research Group at IBM Research Brazil and is also affiliated with the Center for Artificial Intelligence at the University of São Paulo. Having completed his PhD at MIT Media Lab, Dr. Pinhanez joined IBM Research in New York. There, his work resulted in not just Best Paper awards, but also patents. When IBM Research Brazil was founded in 2010, Dr. Pinhanez joined the research efforts there, specifically focusing on research and innovation management. The projects that Dr. Pinhanez is currently leading are aimed at advancing the state of conversational systems, the latter being the topic for today.
Well, first, thank you for the nice introduction. I think here's sort of a summary of that. I think, but I think most important, I'm going to try to bring to this talk the perspective. Someone has been 30 years working with AI and human-computer interaction, and the intersection of the two. And that I think it's important because there are a lot of themes that come back, and that there are things that were discussed in the past that have a lot of history and tradition, and we should know what happened there. But today, what I'm going to try to do is to really look into how conversational systems have evolved in the last 5-10 years, which is amazing how much they evolved. And in the first part of the talk, I'm going to look into specific issues that sort of older systems had, and how they addressed. And I'm going to show some results that my team had in the process as examples. And then the second part of the talk, so I'm going to focus more on these large language models that are becoming popular, and some issues that they bring to which needs to be solved for us to get that into practice. Okay, since I belong to two different institutions, I'm going just to flash a little. Say first, I belong to IBM Research, specifically to IBM Research Brazil Lab. This part of the large IBM research area, which is the scientific arm of IBM. We have about 100 people here in the lab in Brazil. I'm also part of the University of São Paulo Center for Artificial Intelligence for the last 2 years. It's probably now the largest AI research center in Latin America. About 100 faculty, 100 students. We have and working in different areas, and a lot of what I'm going to talk about is in the context of these two structures here. I'm going to start talk a little about what kind of errors we see in conversational systems, and especially two types of errors that existed a lot in the past, and one that's appearing now, which is what I call weird errors. We hear a lot about all kinds of conversational systems, but if you look into practice, into the chatbots that have been deployed by companies, government, and so on, they mostly follow this structure. It is also true for Alexa, for most of Siri, and other virtual systems like that. They are structured as one piece which does what we call intent classification. Given what the user says, what kind of question was that, what we call intent. And then we have the another part that given intent, it generates an answer. And that goes to the end user, and the user answers, and so on. And interesting enough, most of the complexity in terms of artificial intelligence is just in the first part. So to do intent classification, we use very complex neural networks, deep learning, blah, blah, systems. But when it comes to generate the answers, a lot of that is just handwritten by people, or those are pre-written answers or templates that are doing that. And that has implications in terms of what kind of errors we get. So when we have errors in the intent classification system, what we tend to have is what I call wrong errors. So that means the user asked a question, it was not understood by the system, so it classified as the wrong intent, and therefore the wrong answer is generated. Okay, and often when that happens, the end user notice that it got a wrong answer and gives sort of an inconsistent user experience. But another type of error just is when there are issues with what people wrote as the answers. Maybe they are the wrong tone, maybe they have issues of bringing gender or racial issues to play. And those are mostly errors that I call inadequate, that in fact they are design errors or design problems of the conversational system, okay? And that leads to a different issue with the user experience that becomes inappropriate. It brings confusion to the end user to what kind of system of illicit issues like sexism or racism or things like that, okay? But this is sort of the past and present of conversational systems, okay? What we are seeing right now is the appearance of these large language models like GPT-3 and BERT and all this stuff that you probably are aware of, which they go end to end. They recognize and generate at the same time, sort of similar to what translation systems do. But they are monolithic systems. And besides the other two kinds of errors, they introduce a new kind of error, which I would call weird errors, which is they produce good text, but there is something weird about, something wrong. Some people call this hallucinations of these models. It's good language, but it's incorrect language. And I'm going to use as a visual representation of this to help us. So we have seen a lot of these systems that, given a sentence, generate an image. So imagine that the sentence was given a cyclist riding up a mountain. The left image is a correct answer. The right image is what I would call wrong. It's not a cyclist, okay? And but when I say inadequate, I put that image there saying, well, there is something there that maybe it brings other issues, you know, of sexism, of a view of in this case of women, that's not the goal of that thing. And the right one is one that's generated by one of those new systems, where you see that it's weird. It's not really a cyclist. It looks realistic, but it's not a person. It has too many legs. And that's what I mean, a different kind of error, which has often this magic quality. We'll see some examples from tests in other cases. Okay, so what I was going to go in this talk is really to go into these three kinds of errors and see what happens when what we know that happens when they happen, especially in the first two cases, and how can we mitigate some of them in the wrong and inadequate case. In the case of weird, I'm going to talk a little about how can we possibly handle, because I think the research in this area is very limited, I would say, or less at this point. Okay, so but let's start with inadequate answers. And when you come to inadequate answers, often, as I said, because this is pre-written by people, it is a design problem. Those are often the result of poor design choices. Okay, so remember, that's the situation we are looking at. The system understood the question, but something went wrong in the way the answer was written by someone. Okay, and for that we have to understand the following: is that when you go to a professional chatbot, okay, and that can be text or speech, but the people who write the answers is a group of people. Often that involves development team, involve people from customer service. It often involves few people from marketing. Sometimes you have to refer to legal people. We have to see if you can say something or not, or what's the way. And from this committee comes this writing, which often reflects this multiple heads and the lack of agreement, and brings often a lot of inconsistency in practice. Okay, we also have to notice that any professional chatbot involves a lot of curatory work, because any new problem has to be defined as a new intent, as a new answer, and so on. So just a lot of people has to be maintaining. But in a lot of what we're going to see here is issues that involve design decisions. For instance, how much human this agent should look like. This conversation, what's the gender, what's the age, what's the style of language, and not only making the design decisions, but make them be reflected in the actual text. I mean, sometimes they make a decision like, oh, I want this to be sound like a young person, but you just cannot write that way, especially because there are people who are writing a combination of people. And it's also interesting because one thing our research has shown to us is that the perception of these chatbots is really affected by small factors, as you're going to see. Okay, so even small stuff change the perception of people of your chatbot. And that makes the generation of inadequate answers even more common than we think from a user's perspective. Okay, going to give an example of that. Okay, so you're designing a chatbot, and you have to decide which font, which typeface you're going to use for the chatbot. Okay, this very small decision. Okay, and you ask, oh, how that's going to affect the perception of that chatbot. Okay, and we have done this work that we published in CHI 2017, where we shown people a conversation happening in a financial chatbot, and we showed them different versions of this conversation, not comparing, but different situations. And the only change from one moment to the other was that we changed the typeface of the advisor, and they didn't know about that. And then we asked, is this a dialogue between a human advisor or with a bot advisor? And people who are doing this thought they were actually doing this comparing this, but in fact across the different participants or the same dialogue. So the only difference was the typeface. And we saw that the typeface, if you use OCR, which is a machine-like typeface, people would say more that they are talking to a machine just more because of that. And we didn't see that for the Bradley typeface, which was when we pushed towards a human more typeface. That was not statistically significant, but at the same time, we found people saying things like the bot say they thought we are cheating them. You're trying to hide, trying to make it look like too much. So maybe the problem here is that Bradley is too much human, and there's a reversal effect. But anyway, you decided that the typeface decision will affect how people perceive your chatbot. That's the bottom line. That's how delicate this is. Okay. Most recently we finished a study looking into should a chatbot use formal or informal language. Okay. And there are precise ways to define formal and informal language from linguistic. And often when you see these books about designing chatbots, they say one thing or the other without any evidence for that. So we'll decide to say, okay, let's compare this. And we wanted to compare both in the sense of between people and machines and speech and text chatbots, okay? And we framed this experiment as, for our participants, these are crowdsourcing participants, we framed as we have to choose between candidates or between systems for a particular company. Okay, they're not being asked about formal and informal language. They're being asked about which person here which candidate in the selection process we would do. The only difference is one uses formal language, the other doesn't. Okay, and this was in the context of customer service, Brazilian, Portuguese, and what we found is that basically there is no preferred formality for customer service. I mean, it varied a lot, which makes us think that it's very task specific, it's very context specific. There's no general rule. But at the same time, we saw some consistent in the case of machine systems. And we didn't find any difference for speech and concerning gender, also not. But we found sort of was different for female and male text. Remember, what's the difference between female text chatbot and male text chatbot? It's just because we told them that the one was male and the other was female. There was no other difference for the participants. It's not like speech where you can, and that was enough to have different preference. I mean, they preferred informal female text and they preferred formal male text. Okay, and interesting enough, we didn't find that thing for humans. So that old idea coming from Clifford and Ness of oh, what happens to with human beings is replicated for machines. We didn't see in this study. Okay, and in the end, basically, what we found was this little preference for female text, for informal and male text, but basically the basic result here is do for every case, do that. You have to decide in formal and informal language what's the most adequate is most likely a case-specific situation that you as a company will have to design, try, see which ones get better response for your criteria and do it. Okay, that's our overall conclusion here. Unlike a lot of what some of these design books for chatbots say. Okay. We also have looked into situations where the agents are embodied in different ways. So let me just explain what's the situation here. About 4 years ago, we did an exhibit at a gallery, a cultural center, where people would come to a space and talk to characters from a book, a very known book in Brazil. So these characters were supposed to be sitting around in this coffee table. You could ask questions in a tablet, and they would project the answers. The answer would go around the table. This was a nice space, and we had about 10,000 visitors. And what we looked and say, suppose that the characters use your name in the middle of the sentence, what we call direct address. Okay. And this is because when you enter the system, you just say what the tablet would ask your name. So we had the name of people. When we just say some people would see it, some didn't. And And the way we measured user engagement was, because we didn't want to disrupt the experience too much, was basically we looked into how many out of scope questions were asked after you first saw the direct address, okay? Which is a way to directly measure user engagement, very non-disruptive. And we didn't see an effect. Basically, we didn't see an effect of doing direct address in this system, which is also something that some people recommend in design. So basically for this environment was not, it's a good question if this is true also for maybe a mobile chatbot, but it's was interesting that, and it's an important question, is that, does that help? Does that affect or not? So these are some of our experiments related to adequate, and there's a lot of other stuff. I would say if there is one conclusion of all that is, it's more delicate, it's more context than expected. At the same time, people read a lot in all the decisions you make about gender, appearance, font, and so on. And it affects the user experience. But let me look into the issue of wrong for a moment here. And this is the type of error that happens when the extremely complex stuff there, the AI breaks and say, people asks, what's the balance in my credit card, and the system understand that they want, I don't know, that balance is another thing, and answers, oh, you should not apply for this kind of credit. So people get the answer, they understand that that's wrong most of the time, and that creates what we often refer in the field as a breakdown in the experience. Suddenly they were engaged in conversation and say, this other stuff doesn't understand what I'm saying, and they engage in all kinds of repair strategies. Remember the exhibit we did in the museum? There was a situation where we wanted those people only to talk with the characters based on things they have said in the book. Okay, we didn't put anything in the mouth of a character which was not part of the book. So often people would ask things that the systems were not, the agents were not designed to answer, and they would try to deflate the conversation, saying, "Oh, more coffee," as a way to pretend to ignore the error. So this was the typical breakdown in this situation. And what we found is, the moment that they had a breakdown, then they start to have more breakdowns. So and that's one thing that other people have noticed in other studies in different contexts, that the problem with wrong answers is that they lead to more wrong answers. And having a strategy to deal with a wrong answer often is very important to have, because it really corrupts the whole experience from that point on. We found it very significant here. There's other studies. So that's the problem with breakdowns. It gets worse, okay, as you go. And this is another work that we did with the people from IBM in Brazil, which also involved breakdowns in a different way. So let me just tell you a little what this was about. This was work we did with in a museum, and there was an app where people could ask questions about artistic works, from 7 different artistic works, different genres, different periods. And in the beginning, a lot of what was put there was about facts. I mean, who painted this? When was that? And what they quickly found was that people didn't want to get facts from this agent. They want to know about more complex stuff, about what we call meanings. Okay, so for instance, people. What's the meaning of this picture, or who is this character? Things about which are not the traditional factual artwork, author, that kind of stuff. So based on that feedback, those breakdowns, they they increased the basis of answers to the point that the system became would provide a good enough user experience. And when we evaluated the final the profile of answers of this system, I mean, this is about 5,000 sessions or 5,000 users. 60% of what was asked was about meaning. Okay, it was very interesting. People were having very intimate conversations. They thought it was a space to ask difficult questions, not easy stuff. Okay, and I think there's a very important lesson for anyone trying to work with art exhibitions, that the moment that that you create a space, and it's interesting because it's a non-judgmental space. Okay, you're not judged by the kind of answer asked. You can ask, quote, stupid questions, but often stupid questions are effective hard questions about the artwork. And in our case, we saw 60% of those of the time people are interested in using the system to do that. Okay. But remember that the way you arrive there is by looking at the breakdowns and say, okay, this kind of question needs to be answered, and you go on. Dealing with wrong answers is a necessary part of any chatbot construction. Okay. So this is traditional stuff. Okay, what I covered so far is what I'm saying, what's being used right now in most conversational systems. I mean, and what has and some of the difficulties that we still have with those systems. But this is changing, and I'm going to talk now about what's coming and the new kinds of errors, the new kinds of difficulties that we are going to face, in my view. Okay, and this has to do with these large language models. So first, I want to give you a little quick 5-minute introduction to what's a large language model, what's different, what's not. Okay, if you look at the extremely complex stuff that's used that I put there, which is getting even more extremely complex, but it is most of the stuff that's used for intent classification is neural networks, which is this kind of complex math functions that, given some input, I put here the image of a cat classified, it could be a user sentence and classified intent. So this involves, often thousands of parameters. It's a math function, and well, it's great technology. It has led us to all this, but it has some important issues. First is need a lot of computing, need a lot of label data, traditionally have a fixed number of inputs and outputs, and there's a little more technical, but suffer from what we call the overfitting course. The more parameters it gets, after a while it gets worse, and should get worse according to traditional data science. Okay, and well, we have the last 5 years, 5 or even or 10, we have started to solve some of these problems. The first is computing, and this was solved very early in this, has in fact led to this, to what we are now, which is basically we use hardware. We start using graphical processing units designed for doing graphical rendering to do speed up. Now we use dedicated hardware. Deep neural networks are very good for hardware, this kind of hardware optimization, and that's sort of where we are. A very important issue, has to do with the need of label data, is that the last 10 years we had a lot of progress, so especially in language, to understand how to encode better the output. And imagine that you're doing this idea of I have to put as input an image of a cat. Instead of putting the values of each pixel, what I have learned is that when we encode it in a way that captures the variety of the input, with what you call often an autoencoder, the performance of the neural networks get much better. And a common trick is this, where we do an autoencoder where you train it with with a lot of unlabeled data, basically to give an input comes to identical output, but you compress the number of parameters, and you ask some special stuff for this middle, and then you use that half of that network as an autoencoder. Okay, this has incredible impact in the neural networks, but most importantly, it allows us to use unlabeled data in large amounts, which is very important for large language models, which basically are a result of this idea called this technique called transformers, which also solves another problem, which is dealing with a sequence of inputs and outputs. Traditional networks have a fixed number of inputs and outputs, with transformers with this encoder, decoder. You encode, you push your sequence of inputs. It generates a compact, complex representation, and the right side of the figure shows this kind of complexity. Not going to go into details. This very complex encoding of a sequence is used inside the decoder, and then you train the decoder to do all kinds of stuff. Often taking another sequence as input and generating some kind of output. Transformers cleaned up this whole process. There was another of alternatives. There's a lot of people trying to deal with issues of encoding, but basically solved this issue. And last, overfitting. Say, oh, large language models that allow parameters should not overfit. Overfit is this problem that's common in data science, that if you have too many parameters in your function, you tend to find a way, like in the middle one, that you pass right through your training data, but you do a lot of wide stuff. And there has been some recent theoretical work that has shown that neural networks, especially deep learning, do not overfit. They pass through overfitting phase as you increase the number of parameters, but if you increase even more, they leave that overfitting phase and go to a smoothing phase. And that sort of explains why models like these large language models can live with thousands of parameters, okay? Can help us explain, I mean. Okay, so large language models have, they combine all these advances and say, hey, you can put a huge number of parameters inside GPUs without encoders to run with unlabeled data and deal with sequences. And they start to appear, BERT, GPTs, and T5, and a couple of Chinese models. And the number of parameters starts to go to billions. Okay, we are talking now hundreds of billions of parameters. You need 80 GPUs just to run the system, this kind of crazy stuff. And the problem is, the bigger, the better. And there's a lot of studies showing the more parameters, the better your system performs. Okay, the right here, I mean, the accuracy in this case for I believe this is for GPT-3, I mean, it more than double as you increase the number of parameters. They have to be big right now. They won't work when they're big, but they have other problem, okay, which we'll look at. And they're really good. They really do amazing stuff. So this is an example of GPT-3 being used to write text, okay? And they're giving this input and just the word it, and generates this. This is about, the input is about the importance of being Twitter, written by someone in 1897, okay, in London. And it generates a reasonable amount of text. Really good text about this confusion about what's Twitter, and good. Well, not always. So these are two good examples of similar tasks. In black, what the system received. In red, what it generated. That's an example of, oh, you are in a dinner party, your dining room is wider than your doorway. So what to do to get my dining table, which is too big for my doorway? It says, oh, you saw the doorway. in half. Almost sounds right, except it should be showing the table. Even that is not a great idea, but so it fails to get the common sense of what of the problem. Okay, the bottom one is about mixing cranberry juice with grape juice, and you are thirsty, and you drink it, and you are now dead. That's what the system said. Okay, so that's what I call weird. It feels, if you go too quickly, you don't even notice there, and suddenly it's there. And it's similar for these very popular systems that now of giving caption, it generates an image, and these are great examples of nice generated images. These are some not as good as. And I like the left one, that you see that the back wheel is not complete. So it lacks this common sense that a wheel only works when it's complete. Or maybe the image that we have seen before, say, oh, what's a human being? Okay, and so they are great models of language. They are not, they still don't model the world. That's the difference here. And that's why they generate this weird and assimilation errors. And we have to learn how to deal with it. And how do you handle that? And I'm going to give you some ideas, which are also applied to some other stuff in my view, but and I try to do that in the next 5 minutes. So as we said, there's a new type of error, okay? And the problem is there's no way to understand what's happening inside a large language model. Okay, if neural networks are almost impossible to explain, large language models are impossible to explain, okay? So we have to say, okay, those things are black box. In the end, that's what they are. So we have to think they are going to produce weird stuff, and I don't know why, and people don't know why, but hey, these are black boxes. And sometimes people are afraid of black boxes, and I think, I mean, in my view, we live in a world of black boxes, and we know how to handle them, we know how to control them, how to regulate them. I mean, most, you say, how many people know how our power gets to the outlet? Not many. And I certainly have no idea what's going on inside Wi-Fi in practice, or basically anything that has a lot of code. Nobody can tell what's going on just because of the errors. But those are not life and death situations. We go into airplanes, they are big black boxes. In the bottom of the middle, you have an ABS system, anti-brake system. Anytime you press your brake in your car, that system decides if it stops or not you, depending on the sensors on the wheels. Okay. Medicines are black boxes. We don't know what's there. We guess what they do. I mean, physicians to some level also guess what they do in the statistic. And the bottom right is a pacemaker, heart pacemaker, and which is the best example of handling someone's life to a black box. And we know how to control, to regulate, to live them. I mean, we ask, we have a special agencies that test them, that approve them to market, and that's how you deal with black boxes. Okay, which I think we have to do in AI, and even more if non-professionals are using the black boxes. So the left is an example of how we help non-professionals deal with the complexity of the black box of energy. The right is, those are shapes, different shapes used for pills in medicine as a way also to help people avoid taking the wrong pill when they are doing. That's how you help people. You have to be careful, and you have to get them help, visual, interactive help, to avoid them to misuse black boxes. That's true also for neural networks and large language models as black boxes. They are a little different than some of those because they tend to be probabilistic. They are unpredictable in the sense that they are right at X amount of time in the best case, and that they are really not understandable to any practical means. But if we apply to LLMs and neural networks the same ideas that we do in everyday life for black box, I think we are in a better shape even to handle these new kinds of errors. And there's this paper that I wrote for a workshop in human-centered AI, and was where I suggest that when we think user interface, okay, this is a user interface, non-professionals, we should do three things to help people to deal with them. One is to expose the uncertainty that they contain. The other is we should help people trust them. And there's a lot of people working on trustworthy AI. I think that's the wrong direction. We have to instill people say you should trust those arguments. It's healthy for you. It's good for you. And also, this is a little different from that paper. It's a more recent thing. We should avoid imposture. Let me just quickly look through that. Exposure uncertainty is related to make sure that people understand that there may be errors in the answers, and this is something we do all the time with. Sorry for the Portuguese here. We are in the middle of an election, but when we talk about polls, this is evolution of the candidates in Brazil. We talk about errors. Even in Brazil, it's legally mandatory to say to show that the error of the polling. We talk about margins. I mean, this is a way. Why? Because polls are black boxes, are complex things that have uncertainty. Similar, instill distrust. We should push people to help people to not trust what they do. We have a lot of experience in that. Google search, how they instill distrust by listing multiple options, by not committing to say this is the right one. That's a simple way to instill distrust. Okay, and there are other known ways to do that. And very important, I think, it's avoiding posture in the sense of not pretending to have capabilities or identities which the machine doesn't have. And I think I'm very concerned about this idea of using explanation using surrogate models which are explainable, because first, they don't have the same performance. They are not going to provide the same answer. So you are doing one thing and saying that was because of something else. And that's, for me, it's ethically wrong, but also I think in the end for the user experience that will increase trust and on that system. And you have to understand that imposture is an old thing. It's an original sin of AI. If you look at the Turing paper, the founding paper of this area, it's about a machine pretending to be a woman and fooling someone to do so. So there's, I always thought that was a little of a problem with the Turing test, and we saw that if you know the story of Eliza, this conversational system written in 1996, where he was horrified that people would think that system was in some ways that people would behave as it was human, which was not the intent. Well, let me try to finish. I've explored this in this recent paper that went through the EEE Pervasive Computing magazine about how one of the problems that our conversational systems that leads to imposture is that often they comprehend a lot less than they express. The language they say is much complex than the language they understand. Okay, and you can empirically see that. I mean, for instance, Siri and Alexa will use in their language a lot of pronoun resolution that most of the time they're incapable of doing. That's just an example. And in this paper, I compared this to science fiction depictions of conversational systems, especially robots. And it's interesting because it tends to be the opposite. I mean, the character of Terminator, the really talks bad English, but really understands the complexity of all the human beings around it. And I think this is because the creators of sci-fi movies want to make the people to recognize those characters as machines. And often people with conversational systems of those try to make people believe those things are not machines. And that's a simple way to trick them to do that. My view is that we should try to aim for the middle line, which I think it's the ethical way of doing it. And that's a good question of how that impact user experience. And I have this proposal, which is say one way to do that is make sure that what you hear is what you say for these machines. Okay, that they understand as much, they comprehend. And the simple way to check that is if they can understand their own language. If they cannot understand their own language, you are faking this. I'm going to skip for a moment this and say, okay, so basically, I believe this is an interesting direction. These are these three ideas for user interface, which in the end it is still to one word, which is honesty. I think we have our interface have to be honest to the user about what's behind them. Okay, and that's something that we have used recently in an exhibition for kids. We designed this, and they follow these three principles. They interact with these large robots there, and the robots talk about their uncertainty. Kids, they see them making errors, and they help to correct the errors. And we created this visual in a way that it's clearly non-human and as a way to avoid this notion of imposture. So anyway, first thing I would like to thank all the people who worked with me in these papers, this work. A lot of what's there, what I told you, is from all these people from my team. And I think that's it. We can go ahead to questions.